The beam has a length of 0.5 meters and the weight W. A block of weight 12 Newton rests on the beam at a distance 0.15 meters from the end B. 0.15 here. The beam is held horizontally and in equilibrium by a string attached between B and the fixed point C. The angle that the string makes in the horizontal direction is 50 degrees, and the tension of the string is 17 Newton. State two conditions for an object to be in equilibrium. Okay, theoretical question, do you remember? To be in equilibrium, two conditions. Total force equals 0 and total moments, meaning total torque, equal 0. Those are the two conditions for an object to be in equilibrium. Show that the vertical component of the tension in the string is 13 Newton. Okay, try figuring out how to solve this problem. This question be very simple. You just take 17 and multiply with the sine of 50 degrees, right? What is 17 Newton? The angle is 50 degrees, and the question asked for the vertical component, this one, of the tension. Let's call that Ty, vertical component. So that Ty is simply the 17 Newton multiply with sine of 50 degree. With the tension 17 Newton and the angle was given 50 degree. The question asked for the vertical component. That vertical component is this one, the opposite side of the triangle. Yeah. Sine 50 degree is opposite over hypotenuse. Opposite is the Ty vertical component, and hypotenuse is the 17, the tension. So Ty is 17 times sine 50 and approximately equal to 13 Newton. Probably exactly equal, not approximately. Okay, question C. By taking moments about the N8, calculate the weight of the beam. Moments about the N8, calculate the weight of the beam. About the N8, 0.35 times 12. How about the moment of the weight, W? You need to calculate the moment of the weight, which is X, which is the thing that we need to find. The question asked for the weight W around the hinge 8, the axis of rotation. The W, the weight, produce a clockwise moment because it's one to rotate this beam in the clockwise direction. Okay, so this is the clockwise moment. 0.35 is distance here times 12, that is correct. And you need to add it with the moment of the weight, also in the clockwise direction moment, meaning the weight times the distance from the weight here to the hinge A, which is half the length of the beam. We know the total length of the beam is 0.35 plus 0.15, so the total length here is 0.5 meter. Okay, so the distance from the weight W to the beam is half of 0.5, which is 0.25.
I have a question. How do we know if it's clockwise, if the weight is clockwise?
The weight is not clockwise, but it's one to rotate this beam downward in this clockwise direction. And the string here is trying to hold it back, not allowing it to fall down. So the tension here, 17 Newton, is producing a counterclockwise moment. Okay, holding it clockwise moment. And that counterclockwise moment of the tension is 17 times the distance, but the perpendicular distance, which is from A here, you need to draw a distance that is perpendicular to this line of the force 17 Newton, meaning you need to draw a perpendicular distance, like a lot of action with the force 17 Newton. From the hinge here, you need to draw a distance which is perpendicular to this one. And this is the X in the moment. Okay, the formula of the moment. And for this system to be in equilibrium, the total of the moment must be 0, meaning the clockwise moment equals counterclockwise moment. So we have this following equation. Okay, the point now is to find x using this triangle. We are finding this side. The angle here is 50 degrees. So the angle here, which is the opposite angle to 50 degrees, is also 50 degrees. Okay, that side of 50 degrees, this angle is opposite, which is x over hypotenuse, which is the length of the beam, which is 0.5 meter. And therefore x is 0.5 times sine of 50 degrees. And then plugging here, and then solve this problem. The only remaining thing that we need to find is w. So the hardest part is this distance x, which is the distance drawn from the hinge perpendicularly to the line of the 17 Newton force. I'll erase my writing, do it again. 9.24 Newton. Check the mask here. 9.2, good. Question D. Let's do that on the next page. Calculate the magnitude of the vertical component, the force exerted on the beam by the hinge. So we have this vertical component of the tension is 13 Newton that we calculated in part B. Weight of this object is 12 Newton downward. The other weight here is 9.2 Newton. Okay, so the sum of the vertical component is 13 Newton upward minus 9.2 minus 12. At the hinge here, we provide another force, which is like this. And we need to calculate its vertical component. Calculate this one. Let's call this force F. So this vertical component is Fy. This is the force of the hinge in this direction. Why do I know that this force must be to the left like this? Because this 17 Newton has a rightward component, Tx like this. So one condition for the system to be in equilibrium is that the total force is 0. The sum of all the forces is 0. The second condition is the sum of all the moment is 0. Remember? Question A. The condition for the equilibrium. And therefore, the force 17 Newton here has a horizontal component going to the right. And therefore, the force of the hinge here must have another component going to the left to cancel out this horizontal component Tx. Okay? And Fy here, the vertical component, must be so that the Fy plus 13, meaning the upward force, equal to the sum of the two downward force. This is the upward forces. Okay? And the right side here is the downward component. So that the sum of all those components, all those forces, is 0. Okay? And from this equation, we can find Fy, which is the answer of this question, vertical component of the force of the hinge. Hey, Newton. Fast calculation, but I need you to do it again, okay? Okay, 8.2 Newtons. Question E. The block is now moved to the closer end A of the beam. This block here is now moved so the hinge, meaning it is closer like at this place. Assume that the beam remains horizontal. State whether this change will increase, decrease, or have no effect on the horizontal component of the force exerted on the beam by the hinge. So the weight of it is still 12, of course, 12 Newton, but the moment of that force is now smaller. 12 times another distance d, which is smaller. The component of the hinge, the component, horizontal component, the hinge, smaller moment, and this is the clockwise moment, and therefore the counterclockwise moment of the tension, which is the only counterclockwise moment. Okay, the clockwise moment of the tension, T now, times the distance x. The distance x that I drew last time is this distance, x here. Okay, so this moment, counterclockwise, must be now smaller also, because it's equal to the sum of the clockwise moment, which is 12 times d here plus the moment, the weight, the weight times 0.25. Okay? So smaller clockwise moment result in smaller counterclockwise moment, meaning the tension now is less than 17 Newton, not 17 anymore. Therefore, for example, it is now only 10 Newton. So the horizontal component here is smaller and result in the smaller component of the hinge force here also. Okay, so the tension here depends on the position of this block, and the force that the hinge exert on the beam is also depends on the position of the block. State. So the question is just state without explanation. So you just need to say that the component is smaller. 1 word smaller. One mark. So in summary, closer distance of the force result in lower, smaller clockwise moment, which result in smaller counterclockwise moment also. Smaller counterclockwise moment means smaller tension. Finally, smaller hinge force. That is a problem about torque. The point where the gravitational force, the gravity, acts on the object. Okay, so it involves some theoretical question like this, requiring memory, like biology. The two blocks at horizontal beam that is pivoted at this center of gravity here, right in the middle, right at the center of gravity of the beam. And we know the masses, the weight of the two blocks, 54 Newton and 2.4 Newton, and the distances. And the system is in equilibrium because due to the support of a string here, the tension is T downward like this, making an angle 30 degrees. By taking moments about the pivot, calculate the tension in the string. Okay, basically it's similar to the problem that we've done. Try doing that. Calculate the clockwise moment and counterclockwise moment. Okay, the force 54 here is counterclockwise. 2.4 here is clockwise. The tension is clockwise, and the distance to calculate the moment of the tension, you need to draw the line along the string here, upward like this, and then from the pivot, draw a line which is perpendicular to this one. So this is the distance x to calculate the moment of the tension. The clockwise moments are the moment of the 2.4 Newton force here, and the moment of the tension, 0.45 times 54. This is the counterclockwise moment. Now write another expression for the clockwise moment. 2.4 times 0.95, and plus the tension T times x. And then calculate x because we haven't known it. Calculate x similarly using this angle, 30 degrees, because it is opposite to this angle, using the sine of 30 degrees. Sine of 30 is opposite, which is x over the hypotenuse. The hypotenuse is half the length of the beam, and the length of the beam is 0.95 plus 0.35. The hypotenuse is half the length of the beam. Yeah, so you see that we need to practice more about this topic, about the moment, because it appears always in the paper 2. Okay, so x is that one. And lastly, plugging x into the equation and solve the equation to find the tension T is 35. Only 35, no need for the decimals because we're taking two significant figures. Okay, 35, checking answer. Turn to 2.2 here. Question 2. Yeah, 34 Newton. 34 Newton. Your answer is 35. It's a bit different. Why? Answer is 34. I think because they rounded many times instead of one time. Tension times sine 30 times 1.3. Oh, 1.3. 0.95 plus 0.35 is 1.3, not 1.25. Also, that's why your result is a little bit different from the answer, but not accepted. Be careful. The next questions are a bit difficult, so yeah, we do that later. I'll make a video explaining this. Probably tomorrow afternoon to complete this question. I'll send a video to you. Now, after fixing this problem for 1.3, and the tension, the final value of the tension will be 34.